this circuit, if the transfer function is known, then this frequency response is analytically calculated. Okay, this is you already know this. This is a simple story. So this is some linear time invariant circuit, and Ts is transfer function of this. You know what transfer function is. Okay, maybe you don't know, but you assume you know it. Okay, so this input and this is output. When there is input, output will be generated. Okay, so suppose R1 is input. Oh boy, I went too much. Okay, we take break, short break after 2 minutes. Okay, suppose R1T is input and output is Y1T, and from no, not this one. R1T is converted into Laplace transformation. Then you have RS, okay? And with this R1T, Y1T is generated, and from Y1T, Laplace transform of the output, Y1S is, this is R1S, okay? So you have a pair of this and input it output, and you changed your input signal. This is R2 R2. Then you converted into Laplace transformation form, and R2S and Y2T is generated, and using the Laplace transformation you obtain this. Okay? And this pair and this pair, okay? You have one pair of this and this pair of this, and they look entirely different. But thing is, the ratio is the same, okay? And this one is way different. This one is also way different from this, but their ratio remain the same. Yet, ratio of this output divided by input in terms of Laplace transformation is exactly same as this one. Okay, so this is called TS. This is TS. So TS is unique. Okay, so if you know the TS, you have complete knowledge about the system, and this is the mathematical definition of this. This is Laplace transform operation. This is integration, but you don't need to take the integration actually. Okay, you just know this, and this is E minus ST, this is the strong attenuation function to ensure this value is converged to something. Okay, if the RT is increasing, then output will be attenuated by this one. So this integration will be finite number, which is very useful. Otherwise, this definition is useless. Okay, same is true here. This is output, and the frequency response is from transfer function. You know the transfer function. You just replace this transfer function with j omega, because this is the sinusoidal response. Okay, S is usually this sigma plus j omega. For the sinusoidal analysis, frequency response, this sigma is 0. Okay, so you evaluate this magnitude of transfer function itself, phase of transfer function of itself, and you evaluate this at particular frequency, then you obtain the sinusoidal response at that particular frequency. If you evaluate this for the band of the frequencies, for the range of the frequencies, you obtain the frequency response of that. Okay, this is nothing new. You are doing this every time. Okay, but think about the meaning of this. You are evaluating this transfer function without measuring anything, because we already developed the concept of transfer function. So transfer function concept is important. Okay, I take 2-minute break and come back here and finish up for 20 minutes remaining time. Okay. we just have 20 minutes. Okay, so okay. This is the later part of this lecture. It's a rather short one, 20 minutes, something like that. This is an extremely simple example. I'd like to just remind what you have been doing, okay, in terms of this concept of frequency response of transfer function. So this is LRC circuit. This is a circuit diagram. And you know, this becomes SL in impedance domain. So you replace L with SL and replace C with 1 over SC. Then you have this. This is the impedance diagram. And you assume this is composite impedance as a single circuit element. And like the Ohm's law, you use as a resistor here. And this is the what? Voltage division. This is a transfer function. Okay? So you are using this all the time implicitly without thinking about the definition of transfer functions and measurement of transfer functions. Because of there's a concept of transfer function, you easily do this. Okay? This is extremely trivial. All right? So this is simple voltage division. Voltage division. Okay, so from that, this is the low pass filter. This is called the first order. Okay, order means number of reactive component. There is one, so called the first order low pass filter. I'll explain why it is called the low pass filter. And transfer function from here to there is this one, and this is standard form. This is called the frequency response form, and this is written in this manner. This 1 over this CR is defined as pole frequency omega p given by this. Okay, this is standard thing. Then transfer function is simplified to this, and you evaluate magnitude of this using this complex variable. It has the real part and the imaginary part. So this is the magnitude and the phase of arctangent. This is imaginary part and the real part. And this is the real part. This is the imaginary part is coming here, and it has this minus sign because it comes in the denominator. And all this thing is very simple. And you have this transfer function here, and this is what? This is the magnitude equation and the phase equation, right? Suppose the VIT of this circuit is this one, okay? So you put 1 here, and this one sine wave at very low frequency, and higher frequency at pole frequency, 10 times pole frequency, and 100 times pole frequency, like that, okay? Then magnitude is the same. There is no phase delay because this is a DC quantity, and at this frequency, this magnitude becomes almost the same as this one. So this one, in terms of dB, 0 dB, like that. This magnitude is this one, okay? At this pole frequency, magnitude becomes 1 over square root 2, which is this one. And in terms of dB, this is minus 3 dB. And the phase delay is this one. You understand this, okay? Go down, okay? This is the table, frequency response table. You may carry this. This is okay, right? But it is inconvenient and it is not informative. This is very, very bad things to carry, right? But there is a most convenient form of representing this is this one. This is Bode plot, representation of frequency response. It was developed guy named Bode. I mentioned him many times, Hendrik Bode, okay? He made many contributions, but he left his name on this work. So everybody knows Bode from this Bode plot. There are many contributions, more important contributions. This can be considered very simple, but value or beauty of this cannot be underestimated. Okay, right? Overestimated. Okay, very profound. The idea is very simple. Separate this into two curves, and the frequency is here, and this magnitude is magnitude of transfer function, and take this one, so change in dB scale. Okay, and at this frequency, referring to the previous table, until it remains very close to 0 dB, and after this frequency, it starts declining with this slope, and this pole frequency, this is the exact value, is minus 3 dB. Okay, phase, this is the pole frequency. This 1 point of the pole frequency, phase remains almost like the 0 degree, and 10 times larger than this pole frequency, phase reduces this minus 90 degree, and we draw this linear line here, and this is the exact curve. There is some deviation, error, but we already know this, there is an error. This error is very small, negligible, and also we predict in advance, so this is predictable. Okay, so this is called asymptote, magnitude asymptote, and this is also called magnitude asymptote, high frequency asymptote, low frequency asymptote. So they met this point, and you draw this smooth line, and we need this 3 dB difference. Then just sketch this. Then you cannot tell the difference between this and real Bode plot. Almost the same. Okay, and the maximum error is this one, and we exactly know the maximum value of the error, magnitude of error, and the frequency of error. Okay, so it really doesn't matter, something like that, right? And this is the linear, this is log scale, so 10 times increase. No, this is linear scale, 10 times, 10 times, 10 times, something like that. But this inside of this is log scale. This is 1, 2, 3, 4, 5, like this. If you compare distance, this is approximately the same. So this 1 decade is separated into 3 pieces. This is the 1, 3, and the remaining numbers are all packed together. Okay, so this is the Bode plot of this circuit. If you take a look at this, the sinusoidal waveform is here, then it passes not attenuated, untouched in magnitude, because this is 0 dB, but this high frequency sinusoid waveform is applied here, then it will be attenuated by minus 40 dB, which is 0.01 in linear scale. So high frequency component is way attenuated, and the low frequency component is passing unattenuated. It's called low pass filter. So this is low pass filter, and this frequency is called, there is a 3 dB down here, or a 3 dB error called 3 dB frequency, and also called corner frequency, because this has corner, okay, and pole frequency, breakover frequency. They mean the same thing, okay, same meaning. You are using the different terminology. They are the same thing, okay. Let me discuss this second order low pass filter. This is SL, and 1 over SC are, this is the second order, because there are 2 reactive components for system. Order is second order. So from this division rule, voltage division rule, and from that, this is converted into the standard form. This is called frequency response form, or standard form. And this omega naught is this one. Okay, you can easily convert this into this form, and this is the pole frequency. It's not a resonant frequency. Resonant frequency is something else. I will explain that later. In particular, this is called the double pole frequency. because the two poles occurs as a conjugate to pair in complex plane. One here, like that. Okay? So double pole. And QP is quality factor given by this equation. All right? You may think this Q, definition of Q is, there are many variations of this. You got confused. Q here, Q there, or something like that. There is only one definition for the Q. Okay? The only definition is it appears in the electric circuit or mechanical system and whatever systems. Okay? The only one definition is this one. Q is proportional or same as proportional. Is the more appropriate. This is stored energy. This is, and stored energy divided by dissipated energy. Consumed energy. For our electric circuit, this energy is stored, this L and C. Okay. For the mechanical system, is something else. Some mass or some rotating thing. Okay. But definition remains the same. Q, okay, let's take a look at this. Q is here, okay, R is here. If this is small, Q becomes large, okay? That means no power loss. For this case, if R becomes larger, and becomes infinity, it's out here. There is no power loss, okay? Then Q is infinity. So R infinity implies Q P infinity. So R should appear here, right? And why this is C and L, not L divided by C. This is C divided by L because R is resistance, L is reactance, and this is 1 over SC. So this is admittance, but if it goes down, it becomes reactance. Okay? So we have this reactance squared and the square root. Then dimension of this is R. Dimension of this is R. They cancel. So this is a dimensionless number. If this thing is opposite, something is wrong. Okay. Let me take another look. Another example. Suppose you have this series connection of this thing. This is what? Equivalent circuit for the practical inductor or capacitor. So L is here, C is here, this is R. Okay? Here, this is the double pole frequency. It's the same as the previous one, but Q here is this one. Why is that? You can immediately see this is okay. This is a correct expression. When R is 0, R becomes 0, then they are shorted. There is no energy loss here. Okay? So R is 0, then this becomes infinity. That makes sense. Right? That is definition of Q. So you don't remember this. You don't memorize this. Okay? It depends on the circuit diagram, structure of the circuit. Q. Definition remains the same, but this formula will be changed all the time. Okay? But this one is invariant for any cases. Okay? And R is in the denominator. Then this is what? Reactance. This is, I don't know, susceptance or something. It goes up. So this is impedance, and this is impedance squared. And the square root here is R. This is the same as the R in terms of dimension. So again, you have dimension, this number. So this is just the quality factor, a number. Okay? That makes sense. Okay? And whatever circuit you have, you can adapt this approach. Okay? Otherwise, you can, if you start remembering this, you can easily confused. Right? Just remember the definition. The basic concept. behind the definition. And okay, this is something else. And this is you replace this with j omega, s with j omega, and this with j omega squared. Okay, then you have this one, j squared becomes -1. So this is the equation for the frequency response evaluation, and the magnitude of this is this, and the phase of this is this. You can plot this, right, numerically, but that is not for the job for the man. This is for the computers, right? So this is the exact plot. So this goes like this, and it shoots up this one. This is proportional to Q, value of this, okay? If this becomes infinity, this goes to infinity, like that. Okay? And this is double pole, because of the double, so this slope becomes minus 40 dB per decade, rather than minus 20 dB per decade. 2 is important, okay? And the magnitude equation is this, and this phase equation. This is real part, this is imaginary part, arctangent, and because of it comes in the denominator, you have a minus sign here. So this is the exact plot, okay? But don't plot this, don't use this, okay? I remember I asked some take-home questions exams, just sketching this, and one guy used some program to plot this. That upset me, right? Don't use computer to plot this. Use this asymptotic plot. This is called asymptote, and asymptote connect. And you know this, there is this peaking and this frequency, everything. And at this frequency, 40 dB attenuation, 80 dB attenuation, and the phase is changing rapidly here, okay? But at this frequency, this is exact value. At this frequency, this is the exact value, okay? There are only one point where we have the exact knowledge about the magnitude and the phase, all right? Okay, I think I have something to say here more than this. Okay, maybe in next lecture I explain something, some small things. Okay, you need to know about this second order Bode plot. Okay, this is very important, right? Because all the feedback system can be approximated to this form later on, okay? And our case is also true. So when analyzing the power stage dynamics of a converter, knowing this is very important, right? Okay, we stop here. Thank you. Thank you for your attention.